Back in 1993, I had to replace my furnace. It was just a year after I'd moved in. The furnace wasn't working well during the winter, and I got really suspicious, so I had it inspected and it got red tagged. So I had to come up with a new furnace, and I wanted a more efficient furnace. And I was frustrated with trying to work with contractors, so I came up with my own method of figuring out just how big of a furnace I needed. Next, please. Thank you. I want to be clear that I'm not a homeowner. I'm just a homeowner. I'm not a heating contractor. So check this stuff out for yourself, but I'll share with you what I did and it worked out for me. Next slide, please. My method simply uses the data that's provided on fuel bills from CenterPoint, and that tells you how much heat was actually delivered under certain climate conditions. And this method extrapolates from that to determine what furnace size you actually need. First of all, some terminology. CCF, or that's the way they used to talk about it on bills. That's 100 cubic feet, which amounted to about 100,000 BTUs, or what's called a therm. They're still measured, your gas is still measured in 100 cubic feet. And then there's a conversion factor to tell you how much energy was actually in that gas. A British thermal unit gets kicked around a lot. That's used for evaluating or measuring heating equipment. Furnaces are typically quoted in terms of how many thousand BTUs they can deliver per hour. Actually, how many thousand BTUs they consume per hour. So an 80,000 BTU furnace consumes 80,000 BTUs worth of gas. And then based on its efficiency, it delivers a fraction of that, most of the whole of it, to your house. But a British thermal unit, just to put things in perspective, is about the amount of heat you'd get from burning one wooden kitchen match. Heating degree days. Heating degree days are used by the government, and they're used for a lot of different purposes to calculate energy consumption. It is a simple formula. It's simply the temperature subtracted from 65 degrees, which is when you start to need to heat. When the temperature drops below 65, your furnace kicks on, and the amount of heat you need is linearly proportional to that heating degree days. So a average temperature day of 30 degrees is 35 heating degree days. So my formula that I used to calculate the size of the furnace that I needed was simply to take the number of therms that are stated on my bill times 100,000 to come up with BTUs, times the efficiency of the furnace, divided by the heating degree days. This gives you the amount of therms you need per heating degree day, or rather the number of BTUs you need per heating degree day. And since furnaces are measured in BTUs per hour, I divide by 24. And then this last number is a funny little number. It is the temperature rise. So for example, if the temperature is 30 degrees, you want the temperature rise to be 35 degrees to bring it up to that heating degree level. I used -50 as the coldest possible temperature I could possibly imagine ever happening in the Twin Cities. And so I came up with a temperature rise number of 115 degrees. Next slide, please. So here's an example of what I get on my bill every month. This one is my December bill. And at the top, you see what the billing period is. That's when the meter was actually read. And then the first number there, the 196, that's the 100 cubic feet times the therm factor, which gives me a consumption of 233 therms. Now that's for all the use in my house, including heating water and cooking and drying clothes, the other uses I have for natural gas. Down at the bottom, you see total therms used, 233 for the month. The average daily temperature, 17 degrees. So again, using that heating degree day formula, you take 65 minus 17, and that comes up to what, 43 degrees, 43 heating degree days. And it tells you how many days are in the billing period, which is useful as well. Next slide, please. All right, here's an actual example. I'm working out the data on this one. This is from this year, January to February. My bill was read, or my meter was read on the 11th of January, and then again on the 10th of February. And so I took the next bill as well, and I took all those numbers for it and calculated what the average temperature was. Now, the average temperature is simply the high plus the low divided by 2, okay? And I wanted to know for sure that the average daily temperature that was reported by Minigasco, showing my age, Centerpoint, actually matched the real world. So I went to Weather Underground, got the data for January and February, took the days that applied for this billing period, this billing window, and actually came up with the same number. 14 degrees was the average. So applying the formula, and here I also in the middle, my therms for cooking and etc. is about 0.2 of a therm per day, or about 6 therms for the month. So I take 233 therms, 233. Sorry, yeah, all right. I'm getting a little confused with my data, but anyway, I subtracted the 6 therms. Maybe I made a mistake there, but oh yeah, I was looking at last month. Shoot, I did make a mistake. Anyway, the numbers work out. If I had started with 233 minus 6, I would have gotten 227, and I multiply it times 100K because that's how many BTUs are in a therm, and I dropped the K. So it's 22,700 BTUs times my furnace is about 90% efficient, divided by the heating degree days for the month, and I got that by taking that average temperature times the number of days in the billing period, 1,530 heating degree days, divide by 24 to convert it to hours, times this heating rise that I need, and I came up with my need was 64,000 BTUs. Now, if I go back and correct it for the number, which should have been 224, this 64,000 is going to be lower than that. So this is about what I calculated back in 1993. I used more data, I was more careful, and I came up with a number of about 57,000 BTUs back then when I was replacing the furnace I had. I had gone back for a couple of years worth of data and pulled that all together and guessed what my furnace efficiency was for the big old furnace that used to be in the house. The old furnace was 145,000 BTUs input. And assuming it was about an 80% efficient furnace, it was somewhere around 105,000 BTUs of output. And that's what the heating contractors wanted to put in my house. Now, there were some problems with that, and we'll get into that later. But the next line in here tells you what number you would come up with if you had an 80% efficient furnace. Instead of 0.9, I used 0.8. And then I have a heat pump now. That's a recent addition to my house. And it's set up to run whenever the temperature is 34 degrees or higher. So one of the questions I had is how much heating do I need in that heat pump in order to be able to heat my house when the temperature is 34 degrees. And you can see using just a smaller rise that my need would be 15,000 BTUs. Next slide, please. So the typical ways that heating needs are calculated by contractors is to look at how many square feet you have, and if it's all on one level, that's one calculation. If it's 2 stories, well then you don't have to heat the floor between the floors, and so you have factors for that. You have to look at the insulation quality, look at the quality of the windows and how many of them there are, how many doors you have and how good are they. And you have to, of course, take into account the temperature rise or the climate conditions. These can get really complicated, and my contractors really didn't want to do that. So they just said, well, you had 145,000 BTU before, we're going to give you 145,000 BTU as a replacement. You can go out and you can play a little bit with some of these online calculators, and this is just one example, which I put in some rough numbers for my house, and guess what? It came up 105,000 BTUs. Not very good. Next, please. All the contractors gave me estimates to put in the same size furnace for one big reason, that contractors never get called in the middle of the night because a furnace is too big. But the problem with that was my furnace had been short cycling. I actually have 3-zone heating. And so it would turn on to heat just one floor. It would complete that in about 5 minutes, and then it would shut down. So you get these bursts of heat, and then it would cool down. It was uneven. I don't think it was very efficient running that way. It was far too big for the ductwork that they put in the house when you were only heating one floor at a time. And when it runs where it starts and stops frequently, you have reduced efficiency when it starts up, so that overall efficiency of the furnace is less, and it accelerates the aging of the furnace because every thermal cycle stresses the metal, and I think that's why the furnace that was in there only lasted 13 years. The problem with the two was, if they're going to put in another furnace and I wanted a high efficiency furnace, they were going to put in 2 furnaces because high efficiency furnaces don't come that big. The biggest one I could get in a Lennox Pulse, which is what I ended up with, is 80,000 BTUs. And I wanted to see if I could use that furnace. Next slide. So again, a little closer look at this formula. The therms are stated in the bill, and it tells you how long the period is. And then, of course, you multiply it times 100,000 BTUs per therm. You have to understand your furnace efficiency, and there's a lot of factors that can go into that, but you have typically the quoted number from the manufacturer. And a standard efficiency furnace is 80%. I believe that's a law. Heating degree days, cumulative heating days over the period. And once again, that's 65 minus the temperature. And I want to say this about heating degree days. If you keep your house cooler, for example, we heat our house to 65 degrees. So you could lower that temperature from 65 to 58. And then you have a lower heating need. Again, dividing by 24 because furnaces are measured in BTUs per hour. And this worst case temperature rise, like I said, was 50 degrees below 0 to 65 degrees above, 115 degrees of worst case temperature rise. My belief was that I would have the furnace running 100%. And if anybody opened a door, the temperature would drop and you'd have a hard time recovering. But we don't get temperatures like that. So this was my fudge factor, a safety margin to make sure that my furnace wasn't going to fall short of heating the house. Next slide, please. So the heating degree day, once again, the heating degree day is a very simple calculation. They take the daily high and the low and they average them and then subtract that from 65. By the way, there's also a cooling degree day, which goes the other way. Temperature above 65 minus 65 gives you the number of cooling degree days. And as I said, the government and utility companies, they use the heating degree day as a rough approximation of how much energy is consumed in society, and they can plan for that. So it's used both at the macro level and the micro level. Heating degree days presumes a target home temperature of 72 degrees and that an insulated home retains about 7 degrees of energy from other sources, people inside the house and cooking and heating, whatever. But the interesting thing about heating degree days is that they are linearly proportional to your heating needs. Next slide, please. What about furnace efficiency? Well, like I said, standard efficiency by law is 80%. But the actual efficiency of your furnace when it's installed in your home depends on how well your ductwork is designed and whether it's properly running. You know, if you've shut down a lot of vents, you're increasing the duct resistance and slowing the airflow, and airflow is key for heat exchangers. You have also resistance in the filter. You know, some people have gone out and replaced their filter with higher filtration numbers, and that creates more resistance. And if you don't take that into account, you can slow down the air flowing through the furnace, affect its efficiency. And if the filter is dirty, of course, the fan speed is at the proper speed, are the vents open, is the return air capable of flowing easily back to the furnace. Also, the efficiency depends on how much of a temperature difference there is across the heat exchanger. So the incoming air temperature versus the outgoing air temperature. So imagine that, or incoming air temperature versus the flame temperature on the other side of the heat exchanger. So you can imagine that running your furnace at a cooler temperature actually makes it more efficient. And then whether your furnace takes its combustion air from the inside or from the outside. All these things can factor in. Next slide, please. So how accurate is this? Well, it's not very accurate, but it can be improved. First of all, that high-low temperature averaging is crude. You could have 30 degrees and then a cold front comes in and all of a sudden it's 10 below, but that 10 below only lasted for 1 hour of the day or something like that. So it's a crude measure, but it kind of works out in the long run. Other sources of heat can mess with the numbers. So if you're running electric space heaters in the house, then you're not getting all your heat from your furnace, and this method isn't going to work. I said that I have an air source heat pump, and that's really complicated to figure this kind of a thing out because they have varying efficiency or coefficient of performance, as they call it. So you might have to try and figure out how to subtract that out. And again, accounting for other uses of the fuel, that's a crude measure. Mine is about 2.2 therms per day. But if you use as much data as you can find over as long a time as possible, plot it out, and then try to fit a line to it. The slope of the line should match these formulas. And if you extrapolate that slope down to the coldest temperature, you can come up with the same numbers. It is still, I think, better than a lot of other methods. So I actually used it a second time. I was working at a place that had a coal-fired boiler. It was actually 5 million BTUs. And there was a flood in the basement of the building, and we were stuck late in the season. Winter was coming, and we needed an emergency heating system. I used the same technique, but that coal-fired boiler, actually, I had to call the coal supplier and ask them how much heat is in a pound of coal and how many deliveries, how many tons of coal had they delivered to us. And again, I swagged the number for the efficiency of the furnace. I figured out that with 800,000 BTUs of basically barn heaters, we could come up with enough heat to keep the building warm through the winter. And the numbers turned out perfectly. Next slide, please. So I have a lot of confidence in the system, but like I said, your mileage may vary, and I'm not an engineer. I'm not a heating engineer. So double check your own numbers. Questions?
So have you had any issues then with your heater, or it's worked for you, like the size that you ended up getting?
So the test was, how much did the furnace run? I kept track of the heating degree days the next heating season. My daughter actually helped me. My daughter was 8 years old at the time, and I enlisted her help to do this little experiment. I wired an electric clock with hands, so it was an analog movement. I wired it to the fan motor. So every time the fan ran, the clock would run. And we would guess that, when it crossed over 12 hours, we could figure out, okay, you have to add 12 to the number. And she would go down and read it and then reset the clock. And she read it every day for a month. And we kept track of the heating degree days for a month. And it matched exactly with what I had predicted. So it actually worked out. And now this furnace is, like I said, was replaced in 1993. And here it is, 29 years later, the furnace is still working. So I only got 13 years out of the first furnace. I got 29 years out of this one so far. It's still working.
Wow, that's awesome.
Well, I think it's kind of hilarious in a way that we're still using the amount of energy available in a wooden matchstick to as a measurement of energy. I had one question for you. You said you have your air source heat pump kick out at 34 degrees. I'm just curious about why it kicks out there. I have some friends here that theirs goes down to about 0 and stuff, but maybe it has to do with the efficiency of your furnace compared to how much energy you're putting into your heat pump. Is that the deal?
That was a decision I made, okay? I knew that the heat pump was going to have lower and lower coefficient of performance as the temperature got colder and colder, because it's an air source heat pump. It's not constant like a ground source heat pump would be. And so the amount of heating value I was getting out per dollar spent was dropping. I also was concerned about the life of the heat pump. You know, these compressors only run so long, and it was going to run longer and longer as the temperature got colder. And so I figured that was going to age my heat pump. And I have a high efficiency furnace. So I figured out just kind of a swag. One other thing that came into play for me was when you, and I don't know at what temperature heat pump does this, but when the temperature of the coils stays below freezing on the outside unit, you have to go through a defrost cycle where basically they reverse it and it runs as an air conditioner for a short period of time, which heats the outside coils and melts off the ice. And then they go back into heat pump mode. So there's a step function in efficiency when you have to go through that defrost cycle. And I wanted to minimize that as well. I was actually trying to go for the lowest carbon footprint, and I made some guesses on where that would be.
Okay. Well, you might not be an engineer, but that was quite an analysis, I'll tell you. That's pretty impressive.
One more thing about the BTU, they didn't define it based on a wooden matchstick. It's actually the amount of energy to heat 1 pound of water 1 degree Fahrenheit when the water is, I think, at 32 degrees.
Okay.
So it has some more scientific measure, although it's still goofy British measurements, right?
Yeah.
Here's another interesting thing. You hear about air conditioners being measured in tons. Anybody know why they're measured in tons?
I do not.
It relates back to when ice was used for cooling. 1 ton of ice takes 288,000 BTUs to melt. And if you divide 288,000 by 24, you get 12,000. So 1 ton of ice is 12,000 BTUs per hour of cooling.